Okay, one of the problems that comes in your activity slash text test activity test is to find an arc length, but the arc length that I am describing there is a little bit different of the arc length that we have been working with, because it's a kind of advanced form of the arc length. Okay, it's almost the same, but let's start to review a brief explanation of what the parametric equations are and how can we find the derivative of these parametric equations. Okay, so let's start with this. And we know in the past lectures that the parametric equations are um, a way to work some type of relationships between variables when the concept of function is not completely met. So if you remember, we had that kind of weird function like this. And if we apply the vertical line test, this obviously will not be a function because we have many values of y for the same value of x. So this is not anymore or any longer a function. So the solution to this is to add a third parameter. Maybe it could be time or other variable, just to describe the position of the coordinate pair of x and y in relation to a third variable t. In this case, t could be time. And then we can say that the time equals 1, let's say 1 second. Xy is x is some value, and y is some other value. Let's say is a value n and a value m when t equals 1. Okay, when t equals 2, maybe somewhere here, maybe here will be time equals 2, and then we have the new variable t with the defined value of 2, and we will have some value of x equals 9 plus something, and y equals m plus something. Okay, so this is the way that we work these parametric equations in those cases that the classic definition of the differential single variable calculus uh, is not applicable. So if you remember, in the single variable calculus, we found that the derivative is the slope of the tangent line with respect to a curve. And once we find that value of that function of the derivative, we can say that this expression is equal to the slope. In this case, if you remember, the slope in your high school age was represented by the symbol m, and that m was equal to the change in x. Let me change here because this is wrong. To the change of x, the change of y, I'm sorry. Let me change this. The change of y, delta means change, divided or respect to the change in x. Okay. So we were looking for the change in the dependent variable and the amount or the rate of change of this with respect to the independent variable x. And the solution for this, or the function of the algorithm that defines this relation, is known as m, or the value for the slope. But how can we calculate the derivative in parametric equations? In parametric equations, we don't have only x and y. We have a third parameter named t. There, we are adding a third ingredient to this recipe, and now we have this parameter t. And sometimes, like to say, maybe most of the times, t will describe the parameter equal to time. And now we have this type of expression. If you see here, we have this x-axis, and we have this y-axis, and this is any relationship between x and y with respect to t. So this point P is the value for y, and the value for x, maybe y will have a function, x will have another function, and t will define the position of the ordered pair between these two at a given time, or at a given time plus delta of time. This is very similar to the example that we were discussing here at the top of the board. Now, to this type of expressions, the derivative with respect to t, because in this case we are not getting the derivative of y with respect to x, we need to find the derivative of both functions with respect to t. And for that case, we need to do a little bit of arrangements there. Now we have the change of y. This is the change of y, and it's described by the differential of y of t plus delta t, because this is the part that belongs to y, divided by the rate of change with respect to x. But in this case, we are adding this value of t. Why? Because x and y are not dependent of each other. Y does not depend on x, and x does not depend on y. Both of them depends on t. So we need to calculate the rate of change with y with respect to any change of t, and divide that by the change on x with respect to any value or delta of t. Okay, that is the basic explanation for this. If we rearrange this expression, we will come to this, which is uh, the change of y with respect to t. This is a value from t delta t minus g y of t. This is the same composition as the old single variable derivative, divided by the change of x with respect to t. And if we multiply that by this 1 over delta t divided by 1 over delta t, mathematically, this is not affecting this expression, because I am multiplying and divided by the same amount. This is just to rearrange the expression. If we do this operation, we will come to this y times t plus delta t minus y of t divided by delta t, divided by x of t plus delta t minus x of t divided by delta t. If we know, this is very similar to the classic definition of the derivative, but in this case we are adding this term, which is the change of t. Now that we have these two expressions arranged in this way, we can calculate the limit when delta t approaches or tends to 0. Why? Because this is the basic definition for differentiation. And then if we add this limit to this part, we will come up with this approaching zero, delta of t approaching zero, and delta t for the second part approaching zero. And this is to give formality to this expression. And that will be equal because this is the derivative of y with respect to t, and this is the derivative of x with respect to t. So if we divide this by this, we will now have the derivative of the parametric equations of two variables depending of a parameter, in this case, t. And the notation that you will find in your textbooks when you see this little variable notation like this y with a little circle on the top and x or whatever the other variable is with a circle on the top, this means that this is parametric. Okay, if you see this is parametric differentiation. And what is this about? Is this is the derivative of y in respect to t divided by the derivative of x with respect to t. So this describing the parametric differentiation, and we will use this expression, and this is the definition and the basic form for this calculation. So let's work an example. We have an example here, and this is x, and x is a variable which depends on t. As you see here, x equals t to the square minus 4, and y is equal to t divided by 2. If you see here, both variables x and y depends on t. So if we want to calculate the derivative of parametric function, which is the y circled divided by the x circled, we need to calculate two derivatives in this case, and the derivative of x with respect to t, which is this part over here, equals 2t, because the derivative of 4 is 0. The derivative of t squared is 2 times t n minus 1. T to the 1 is t. And the derivative of y with respect to t, y is equal to t divided by 2. Okay, the derivative of t is 1, so this is equal to 1/2. Now we have the derivative of y, which is 1/2, divided by the derivative of x with respect to t, which is 2t. And performing these calculations, we will end up with this 1 over 4 times t. And this is the derivative of the parametric expression described here. So as you see, this is fairly easy. The only thing is to connect the first part that you learned in the first lectures with the differential calculus that you were working right at the beginning of your course. So that we are doing now is we need to divide both rate of change. Why? Because we know we are now having these x and y variables depending on a third parameter, in this case, t. So if we want to find the average rate of change of those two, we need to find the rate of change of x with respect to t and the rate of change of y with respect to t. If we divide those two, we will have now the derivative in parametric equations. Okay, I hope this will help you a little bit. I will work now, starting from this point. I will work in my next upcoming lecture how to calculate the arc length in parametric equations, just to don't leave you alone with those two problems that are included in your activity/text. Okay, stay safe.